right, thanks a lot, Nicola, for this nice introduction, and thanks to everybody for having me here today and for coming to this seminar. Yeah, this day was really nice to talk to lots of people here. You're doing really great science, and it's a pleasure, to be around. So today we'd like to show you the work that has been conducted with a group of people that you see here, and they were or are based in the University of Padova and INGV, which is the National Institute for Geophysics and Volcanology. So basically, over the last few years, we have tried to develop a new approach where basically we are trying to combine geodynamic and seismological modeling to better reproduce the earth dynamics and structure. Right, and on Tuesday I gave a talk at the UTIC where I have explained a bit more the details of this technique. Today I will show you more the application of this technique to the Mediterranean basin. So usually, we use geodynamic modeling, as this one, to reproduce the dynamics of a given tectonic setting. But the point is that the solution of any geodynamic model is not unique. Of course, as you vary the parameters, the result changes a lot, and you need to give constraints to this model to say that the model is reliable, right? In terms of reproducing the dynamic evolution of a given the settings, the area that you are studying. And usually we use seismic observation to give constraints to this model. On the other hand, we use seismological methods to reproduce the present-day structure of the Earth interior. Like this tomographic model that I will show you later. The problem is that the interpretation of the seismic observations, like seismic anomalies, again, is not unique, right? And so you need to give some constraints to interpret these anomalies. And usually, it's better to use geodynamic models, right? To try to give a physically based interpretation of these observations. And so this is why basically we are trying to combine these two techniques. And the point is that the geodynamics and seismology are linked because the geodynamic evolution of a given area affects the elastic properties of the medium that we want to study with seismic methods. So we know that when deformation, for example, in the mantle is accommodated by dislocation creep mechanism, fabrics are formed, and specifically the crystals like olivine tends to orient preferentially. This is an example from a real mantle sample. You can see that the crystallographic axis of olivine, they orient in some preferential directions. And what happens basically is that the mechanical properties of the aggregate then will vary as a function of the propagation and polarization direction of the seismic wave. So you can see that, for example, B waves here are faster in this direction, slowest in this direction. This is because the olivine crystals are intrinsically anisotropic. Another very famous and well-studied phenomenon is the splitting of shear waves. So if you have a shear wave that travels to an anisotropic medium, the shear wave is split into components, orthogonally polarized. Usually we try to measure the polarization of the fast component and the time delay between the fast and the slow components. So we know that seismic anisotropy is widespread, at least in the lithosphere and upper mantle. Here, for example, we can see a compilation of the seismic anisotropy observation in the central Mediterranean. We can see with the black bars the splitting of co-refracted SKS waves, and then with the orange bars the fast azimuth of PN waves. So these are waves that are refracted at the MO and sample the top part of the mantle lithosphere. And then the purple bars here, they show the azimuthal orientation of the fast Rayleigh waves in this case, right? So the point is that if we know the relations between the mantle flow, the fabrics evolution in response to deformation, and the type of anisotropy that are that we should expect from these fabrics, right? So basically, we can reconstruct the dynamic evolution of a given area. Like for example here, this is a paper by Claudio Faccenda and Thorsten Becker, where they have tried to basically interpret the seismic anisotropy in terms of strongly three-dimensional flow. The point is that, as you can see, especially for settings like the Mediterranean, the situation is quite complex, right? And so once again, the interpretation can be not unique, right? The other point is that SKS waves, they carry a path integrated information, right? So it's difficult to say where the anisotropy is along the path. So if you want to have a volumetric representation of the seismic anisotropy in your volume, you should apply seismic tomography. However, seismic tomography, usually they ignore seismic anisotropy, right? Because it's very difficult to invert for many unknowns. There are seismic anisotropic models that have been produced, basically assuming that the anisotropy is confined either in the horizontal plane or in the vertical plane, right? But in this case, I mean, you don't really manage to have a three-dimensional representation of the anisotropic field, and so of the flow field. And so the first thing that we are trying to do here is trying to develop a method for inverting the seismic anisotropy in a tilted transversely isotropic medium. A transversely isotropic medium is a medium where the velocities are the same in a symmetry plane, and then gradually vary as the propagation direction deviates from the symmetry plane, right? And the deviation is maximum when they travel normal to this symmetry plane. This is called the symmetry axis. The symmetry axis can be faster or slower relative to the velocity along the symmetry plane. And so for testing this methodology, we have used a geodynamic model of subduction, where we have computed the elastic properties, which depend on temperature, pressure, and so here you can see that the isotropic anomaly is due, velocity anomaly is due to only the cold temperature anomaly associated with the slab, and that's why we get this fast anomaly here. And also we have computed the fabrics as a function of the deformation, and basically we can get for example, the P-wave anisotropy that you can see here in color. This is the amount of P-wave anisotropy, and the bars indicates the direction of fast P-wave propagation. Okay, so then we have computed seismological synthetic, so the synthetic waveforms with the spec-FEM and the axis-M. We have these virtual array of seismic stations which are spaced 75 kilometers apart, which is a spacing comparable to the US array. Okay, and this is the result. So basically, when we do ignore for seismic anisotropy, we do manage to reconstruct to some degree the slab at depth, but then you can see that we get lots of low velocity anomalies all around the slab. These are artifacts, because if you remember, the only true velocity anomaly is this one associated with the slab. And the point is that these low velocity anomaly, they occur below the slab, but even above, where we should expect some fluids melt and so on. And so the point is that these artifacts are quite kind of dangerous, because they can bias our understanding of the deep earth structure. This is instead here the results when we do account for seismic anisotropy and we do invert for P-wave anisotropy. You can see that now the artifacts are strongly attenuated, because of course here these artifacts are due to the so here we are using only teleseismic phases, no? And the fact is that we are sampling the slow direction instead of the other direction, and that's why you get these low velocity anomalies. So here the artifacts gets attenuated, we get still some indication about the shape of the slab, and also we get the P-wave anisotropic field. So these are the P-wave fast directions, which tell us which is the fabric at depth, and so with this indication we can reconstruct the evolution of the system. So basically here you get these circular patterns because the plate subducted, retreated, and the retreat basically works such that the mantle below the slab is evacuated with these toroidal flow cells around the slab edges. And we also, in this vertical cross-section, you can see that we can reconstruct the dipping portions of these P-wave fast axis. So, summarizing, if this is the target, so the fast slab and all the P-wave fast directions around it, this is what we can reconstruct. Okay. So unfortunately here we cannot reconstruct the horizontal portion of the plate. Why? Because we are using teleseismic phases only, and so we are sampling only the vertical direction, and therefore it's difficult to locate these horizontal fast layers. Okay. So we have applied this technique to the central Mediterranean, so where we have a relatively dense array. These are the teleseismic events that we have used, and so this is the result. This is the solution where, when we ignore for seismic anisotropy, you can see that we see at 100 and 300 kilometer depth some fast anomalies which you can relate to the subduction of the alpine and the Apenninic slab, right? And this is a vertical cross section, and this is the anisotropic solution. So the differences here basically is that some of the low velocity anomalies that are present in the isotropic solution, they are attenuated and they disappear. Also here you can see these ellipses, they indicate the P-wave fast axis. So basically the longest semi-axis of the ellipses indicate the P-wave fast direction, and the smallest semi-axis is proportional, the length of the smallest semi-axis is proportional to the dip of the fast axis relative to the cross section. So just want to show you the main differences, right? So the main differences are here, nearby the Massif Central. So while here there is a widespread low velocity anomaly, in the anisotropic solution, this low velocity anomaly is much smaller and is more cylindrical at depth. You can see also here. And below the Calabrian slab, here you see that there is a very strong low velocity anomaly. So this low velocity anomaly is not connected to any feature at the surface, right? And this appears in many other seismic tomography studies. So the problem is how to interpret this low velocity anomaly. Is it melt sitting there, metasomatized mantle? But if you account for seismic anisotropy, you can see that this anomaly disappears. So probably, which means that there is no compositional or thermal anomaly down there, right? So you can see here this cross section in the isotropic solution, you get this strong low velocity anomaly beneath the Calabrian slab, and then isotropic solution, the low velocity anomaly disappears. Okay. Okay, now if you want to say something about the mantle flow, so here the mantle we think that is flowing around retreating alpine slab and around the Adria slab, and toward the mantle wedge of the retreating Calabrian and Aegean slabs. Here this is again flow below the Adriatic around the Ionian plate. Here we can see three-dimensional view of the cold anomalies volumes. Okay. Here the top view of the three main slabs: Alpine, Apenninic, Adria, Aegean, and this is the Alboran actually. And these are the slabs just shown individually. These bars here indicate the P-wave anisotropy at depth, 200 kilometer depth, and here you can see the animation. So basically, you can see that here, this is the Calabrian slab, the mantle is flowing around and then toward the mantle wedge, toward the retreating portion of the mantle wedge. This is the Aegean slab, and you can see that here the fast P-wave directions are parallel to the dip of the slab. This is because the slab is going down and is shearing the mantle above, and this is a standard solution of many geodynamic models, and this is why we get this dipping fabric. Okay. alpine slab, which looks like distorted, and then here the Ionian plate. So you see you have subduction under Calabria, the northern Apennines, and then here there is this big slab hole. This is consistent with other tomographic models and with the recent less than 1 million year old volcan is present in this area. Okay. Yeah, just want to say that now we have done a step further, and we have done a joint inversion of P wave travel time and S wave splitting intensity, which are more sensitive to seismic anisotropy. And I just show you, and for the entire Mediterranean, and I just show you the result from the Alpine area, Apenninic slab, and now we have this new way of representing the fast direction. So with the streamlines, we help basically reconstructing the mantle flow around the slab and in the mantle wedge. Okay, another specialty of the house is geodynamic modeling. And so here, this is a project run by Rosalia Lobue, who is now in INGV Catania. So basically, we have used paleogeographic reconstruction to define the initial setup, which correspond to basically more or less 30 million years ago, the situation 30 million years ago. So we placed a trench here with a 200 kilometer long slab attached to it. This is Africa, this is Adria plate, and Spain, France, right? And these light blue here represent the Ionian oceanic plate. Okay? And what we have done here, we have tried to understand what's the role of lithospheric heterogeneities, because we know that in the northern Apennines, the continental lithosphere is thin, while here in central Italy is thicker. It's probably much stiffer. And so what happened? So this is the evolution, that as the Estonian slab subducts and retreats, the mantle flows around it. And then as it interacts with the passive margin, there is tear of the slab along the passive margin and formation of a slab window where there is this stiff continental promontory, because this promontory is buoyant, stiff, doesn't want to subduct, and that's why you form the slab window, right? And here you can see 4 different steps, right? The other thing is that the trench retreats in the northern Apennines up to the Adriatic coast, which is what we see today, while here, where is the stiff continental promontory, does not, and here, where is the Calabrian arc, there is still subduction ongoing. This is just a parameter sensitivity test. This is what we have seen before. This is when we do not have the thin continental lithosphere here, so there is no retreat of the trench up to the Adriatic Sea. Here, no stiffer continental promontory, so basically there is this entire break off of the slab, and here there is no lateral heterogeneity, so there is an homogeneous Adria plate. Again, there is basically full break off of the slab. So that's why we think that these heterogeneities in the Adria plate must be considered when modeling the evolution of this area. After this, we have extended our domain and tried to include also the Dinaric Hellenic Trench, Alpine Trench, Alboran Trench. And yeah, this is the model evolution, right? So each retreating slab induces flow in the surrounding mantle. There is some tearing, slab break-off, and so on. So when you have this sort of model, once again, you still have to validate their output in terms of, you need to give some constraints, right? And so what we can do here, we can compute the mantle fabrics that develop as a function of the deformation, right, mantle deformation, and with those fabrics, with the PT conditions, we can estimate the elastic properties at each single point of our domain, and then we can perform seismological synthetics. So for example, we can compute shear wave splitting. So basically we assume that the shear waves are SKS waves, which are traveling almost vertically and are sampling our medium along this direction. The green bars here show the synthetic shear wave splitting, and the bars colored from yellow to black, they indicate the true data. This is actually a compilation of data from Torstenberger website. There's a new one was just published, more updated one. So anyway, you can see that in some areas the fit is quite good, while in some areas, especially subduction areas, close to the boundaries of our model, the fit is not that good. The problem is that the model that we have has close vertical boundaries, lateral boundaries, and so there is when you get close to these boundaries, there is interaction of the flow with the boundaries. So of course there are some problems here. But anyway, the average, the misfit, right, between the observations and the synthetics is about 20 degrees, which is an improvement relative to what has been produced so far for this area when assuming steady state conditions, right? So the novelty here is that we are accounting for the dynamic evolution of the system. Okay, but another thing that you can say is that, okay, your P-wave anisotropic tomography technique, how good it is, right? So what we can do, once again, we have the elastic tensor and density everywhere in our domain. We can compute P-wave travel times and then perform the P-wave anisotropic tomography. So this is the target. Again, you can see the fast anomalies for different depths related to the slab. And then here, where there is the back arc opening, there is this very strong low velocity anomaly. This is due to hot mantle upwelling replacing the lithosphere. Now, this is the result with the kind of, we put some noise, 450 milliseconds. And you can see that the shape of the slab, the fast anomalies are reproduced quite well. In this case, actually, we have used the same teleseismic event distribution and array, seismic station array, as in the real experiment, as in nature, right? And you can see that the shape of the fast anomalies can be retrieved, and also part of the seismic anisotropy field. This is when we have we assume that we have a bit better data set with less noise, and there is a slight improvement. This is a completely ideal situation. So here we have assumed that we have stations everywhere, in land areas and marine areas, something that we will never be able to have in the future. But you can see that if this is the case, right, we can reproduce very well the slab shape and the anisotropic field. The only problem is that there is smearing, vertical smearing of this strong low velocity anomaly. Why? Because once again we are using teleseismic phases, and so it's difficult to locate vertically the low velocity anomaly which is at the surface. And so what happens is that the low velocity anomaly gets smeared vertically over the entire upper mantle. Now, if you are interested in this sort of modeling, we have now released this open source software which is called ECOMAN, which stands for Exploring the Consequences of Mechanical Anisotropy in the Mantle. So basically, if you have a geodynamic model, you need velocity, pressure, and temperature fields, right? And then what you can do as a post-processing routine, you can fill up your domain with hundreds of thousands or millions of crystal aggregates with different composition. It can be upper mantle transition zone or lower mantle composition. And then you can use these softwares here in green to compute the strain-induced fabrics for CPO, LPO, and also you can assume that there are some extrinsic anisotropy due to compositional layering or presence of cracks and so on. So then what you get as an output, the elastic tensor, you have density, right, all scaled by pressure and temperature and composition. You can visualize the elastic tensor. So for example, here I'm visualizing the P-wave anisotropic field in this model of subduction. And then I can perform the seismological synthetics. Okay, so I can perform either, I can compute synthetic SKS splitting, or I can perform the isotropic or anisotropic P-wave tomography with this software here, right? And the point is that I can use also this software PSI, which which stand for Platform for Seismic Imaging with Real Datasets. This is what you get. These are three different models. So this is a toy model of a quelling plume. You can see that you can visualize the isotropic VS with the SKS splitting. This is radial anisotropy in color, or the bars indicate azimuthal anisotropy at 200 km depth. This is DVS. This is the amount of reflected energy. So you can compute reflected and transmitted energy at discontinuities, which is useful for receiver functions, for example. This is an example for a 3D subducting slab. Again, radial anisotropy in color here, SKS splitting, and then you can do this also at the global level, right? So this is a model run by Paulomi Roy. This is radial anisotropy, and this is isotropic DVS. Yeah, so basically you can do this exercise for any kind of geodynamic model, 2D, 3D, Cartesian, polar coordinates, regional scale, global scale, and so on. And then what you can do, you can also perform these synthetic tomographies. So if this is your target, this is what you should get, right? If you do the seismic tomography. And this is exactly what you should compare with the observations, right? Because, of course, with the classic seismic tomography inverse methods, deterministic approach, you get regularization. So you have damping, smoothing, right? So you're never gonna get such a clear pattern of your structures, right? But everything's gonna be a little bit blurred. There are some artifacts. These software, the deterministic inverse model has been coded by Brandon van der Beek, right? Who is now in Leeds. And you see that you can also use real data, right? As we did, as I showed you before for the Mediterranean, and now Brandon is working in the Cascadia margin. So this is the Juan de Fuca slab below 100 km depth. These are the low velocity anomaly associated with the Juan de Fuca ridge here, and then this is the P-wave anisotropic field at I think 200 km depth. So first conclusion is that this methodology can be useful to reconstruct the present-day structure and recent dynamics of different tectonic settings. It can be used to validate geodynamic models, yielding a physically based interpretation of seismological observations. We can test advantages and pitfalls of existing seismological inverse methods and the artifacts and how to remove them. And we can test new inversion methodologies to separate the isotropic and anisotropic components of the elastic tensor, which actually these are these new techniques that allows us to account for anisotropy and get rid of the artifacts. Okay, another interesting feature of the Mediterranean basin is that it is characterized by many anorogenic volcanic provinces which formed over the Cenozoic. Okay, so these anorogenic magmatic products were erupted, you see, all around the basin. So anorogenic means that this magmatism is not related, is not arc volcanism, cannot be defined as arc volcanism related to subduction and dehydration of the slab, in production of magma in the mantle wedge. The other thing is that looks like that some of these anorogenic magmatic products, like those here in Western Italy, have some compositionally, they have the smell of some continental component which appears to have been subducted, right, together with the Ionian slab. So how to explain this anorogenic volcanism? So in 2010, Claudio Faccenda and again Thorsten is here. They have proposed that subduction of the Ionian plate beneath Sardinia, Corsica, Spain and France would have induced upwelling at the front of the subduction and close to the slab tip, right? Then the slab retreat, but still is inducing upwelling close to the slab tip because the mantle here needs to, it's sucked right, and pulled over the retreating slab, right? Here you can see the occurrence over time of these anorogenic magmatic products. These markers in light yellow color. Now the point is that upwelling in this way of a mantle that is not thermally anomalous or composition anomalous would not yield any magma. Okay, because if it's not thermally anomalous, yes, the mantle is hotter at depth, but then when it rises toward the surface, it will cool adiabatically. It will follow the adiabat, and nothing would happen. However, if we have, for example, a metasomatized mantle transition zone with a 0.2, 0.3% weight percent of water, which can be easily stored into the minerals of the mantle transition zone, basically what happens is that when subduction occurs, right, subduction occurs and upwelling is induced. So the mantle transition zone rises toward the surface, the minerals transforms into upper mantle minerals, olivine and pyroxene, which have a much lower hydrogen solubility, and magma, partial melting, is produced. Okay, then here what happens is that when we reach a given melt fraction, we extract this magma and we form these volcanic products here at the surface, this one in yellow here. And so as subduction proceeds, you can see that you can form magmatic products at the surface which are very far away from the arc. This is the arc volcanism, the classic arc volcanism that is connected to subduction. And the other nice thing is that upwelling is also induced below the slab, and there is partial melting, and we can extract some volcanics also here, offshore, right, of the trench. Right. I'll keep this running. Okay, so we have what we call anorogenic volcanism, which forms here and also a little bit here. And this is consistent. We have applied this model to explain the anorogenic volcanism that has been observed in northeastern Asia. So where here there are these petit spots that have been discovered over the last 10 years or so. Okay, these are very small volcanic centers that form in the last few million years that are located offshore of the trench. And then these are all the magmatic products that have formed over the Cenozoic here in China. So basically what we have done here, we have tried to apply this model to the Mediterranean. Okay, so again we start with these conditions. This is the initial position of the slab 30 million years ago. We place some wet inclusion in the mantle transition zone, and then what happened? As subduction proceeds, you can imagine that mantle upwelling is induced at the front, and here you start to have extraction of magma and basically formation of volcanism at the surface. Then here there is again formation of the slab window in between the Apenninic and Calabria segments. Okay. Okay, so here we can see 4 snapshots. This is after 16 million years, this is after 30 million years, 35 million years, and again the same but from a different angle. So you can see that we can extract lots of these lots of these magmatic products which are not, cannot be related to the dehydration of the slab. Right? These are due to the upwelling of the wet mantle transition zone. And if we look at the age of the extraction, so this is model age. Okay, so green means the start of the model, and orange means toward the end of the model. You can see that there is a kind of trend here. There is a younging of the magmatism toward the east, which is actually what has been observed in this area, and also there is concentration of the magmatic products along these two lines, which is also a little bit consistent with the observations. And you can see that we have also these magmatic products where nowadays we have the Campanian magmatic province, so Vesuvio, Campi Flegrei, and so on. And the other nice thing is that here, so in white, you can see this is continental crust that has been subducted. Why? Because this margin, right? This is basically the passive margin of North Africa that has been a little bit scraped off and eroded and brought down into the deep mantle. The same occurred here, where a little bit of the Tyrrhenian passive margin has subducted. And of course, if this material starts to melt, okay, we will get some, let's say, particular composition of the erupted magmatic products. And just I want to say that this window is basically what we see also with the P-wave tomography. Okay, so I think I'll have some water before the last thing I want to show you. So after working for many years on the mantle, we have recently we got interested on basically structures that can be found at the crustal level. And so this is a project by PhD candidate Gianmarco Del Piccolo, where basically we have tried to image the structures beneath the Etna volcanic field. So we are in Sicily, okay? So these dots indicate the local seismicity, and the black squares indicate the seismic stations. This is a working collaboration also with colleagues from INGV Catania and Tarragere from 88 Zurich. So for this imaging, we have used a new methodology, which is called transdimensional Monte Carlo inference. Okay, so basically the domain is discretized with the Voronoi tessellation. Each Voronoi cell has constant properties, so constant velocity anomaly relative to a 1D profile and constant P-wave anisotropy. The model space is investigated in a probabilistic way, okay? And so basically what we need to do here is define the priors, so the range of parameter variation for example, P-wave anomaly or amount of P-wave anisotropy, okay? And then what we can do here, we can run tens or up to 112 independent Markov chains, which sample in a probabilistic way the parameter space. Each chain sampled millions of models, okay? And basically at each iteration, what the model does, so basically there are a few options here. You can move the position of the nuclei of one cell. You can change the elastic properties of the cell, so anisotropy or the isotropic anomaly, or you can add or remove one of the Voronoi cell. So you are changing the dimension of your model. That's why this is called transdimensional Monte Carlo inference. So in the end, we have many millions of models, and what we can do, we can compute statistical moments. So the average and the standard deviation, which means that for each point of our domain, we have a measure of the uncertainty. Because if the standard deviation is small, this means that many models need those structures at that point of the domain. And so we are, in a probabilistic way, we are kind of sure that the structures are robust. While if the standard deviation is very large, this area have a higher uncertainty, and we are not basically interpreting these areas. So here you can see the average low uncertainty P-wave anomalies. So here, top view, side view, we have two main anomalies. This high velocity body that goes from the surface down to 6 kilometer depth, and this is usually interpreted, is seen in other tomographies, and is interpreted as the old volcanic edifice, the root of the old volcanic edifice that has crystallized. So you have to imagine this is basalt that has crystallized next to sedimentary units, flishoid units, okay? And so it appears as a faster body. And below it, we have this low velocity body which branches also around the high velocity body, and that has mostly this elliptical shape. The other interesting thing here is when we look at the P wave slow directions. Okay, so these are what we are plotting here are the direction of slowest P wave propagation, and you can see that below the high velocity body there is this cylindrical alignment of the P wave slow directions, and this cylindrical alignment goes down from 6 to about 16 or 20 kilometer depth. Okay, so you can see also here in cross sections at 6 and 16 kilometers, the patterns here is circular, and then here in the northwest quadrant becomes more oriented in this way. Now, if we compare the slow directions with the t-axis, tensile axis of the local earthquakes, you can see that also the t-axis of earthquakes located at from 6 to 16 kilometer depth, they have this circular or cylindrical structure, which is the same as the cylindrical alignment of the P wave slow directions. Actually, this cylindrical pattern is not centered below the topographic peak, which is here, but it is a little bit shifted south in the southeast quadrant. Okay, so we have cylindrical pattern of P wave slow direction, same cylindrical patterns of tensile axis. How to interpret these seismic anisotropy? So let's image that we have preferentially oriented cracks, okay, filled with magmatic fluids because we are in a volcanic field. So the cracks will open, right, in this direction, which means that this is the direction of the orientation of the tensile axis, the sigma tree. Okay, the P wave slow direction will be also normal to the cracks, and so parallel to the tensile axis, right? Because the P wave travels the slowest normal to the cracks and fastest parallel to the crack plane. And so now, if we have this P wave slow direction pattern, and now we plot the normal to these slow directions, we can get the fast planes, which we think correspond to the orientation of the magma filled cracks below the ethnovolcanic field. And you can see that these cracks, they have this radial pattern, cylindrical P wave slow directions. If you plot the normal, you get a radial pattern. This is a 3D animation of these fast planes and the isotropic anomalies. So basically, you can see that the magma appears to be distributed in these cracks all over the volcanic edifice. This is the radius of this volcanic edifice is 20 kilometers. Okay, and this I think shifts a little bit the paradigm whereby magma is focused along some conduits, and then maybe it can stagnate in some magma storages, right? So in this case, it looks like that the magma is really widespread below this edifice, which also would explain why there are lots of lateral vents which get activated quite often on the Etna. Now, how to explain these cylindrical pattern of the tensile axis? So we can use geodynamic modeling, where we can test the effect of topography, tectonic stress, lateral density heterogeneities, and the presence of pressurized magma storages like these. Here you can see this is a very idealized magma storage with a prolate shape, and then here there is the conduit which I'm feeding from below with some magma. So basically, if you feed this magma storage here, you see that the pressure increases in the surrounding medium because you are injecting fluids, and the tensile axis, so the sigma tree that you see here with these bars, they form this cylindrical pattern around the magma storage. The same is obtained if I define an oblate shape of the magma storage, which is also more compatible with the shape of the low velocity body here. You can see that again, if I pressurize this oblate magma storage, I get a circular pattern of the tensile axis. So in the end, so the conclusion here is that it looks like that the crust below Etna between 6 and 16 kilometer depth is characterized by the presence of this oblate magma storage, okay, which is pressurized and that induces this circular pattern of the tensile axis, and in turn induces the formation of this radial pattern of the dikes, which should depart from this central magma storage. Okay, this is my last slide. So I hope I have been able to show you that with this multidisciplinary approach that combines seismological and geodynamic modeling plus mineral physics, we can better study the present-day structure and recent dynamics of different tectonic settings. The present-day configuration of the central western Mediterranean is characterized by multiple slabs with lateral and internal tiers, slab windows and so on, indicative of their interaction with passive margin and final stages of subduction. Seismic anisotropy is likely higher than what retrieved by deterministic inverse model. This is because in the test I showed you before, when you use these deterministic inverse models, there is smoothing and damping. What you retrieve is always a smoothed version of the reality. Okay, so lots of times, or years ago, I was criticized sometimes because seismologists were telling me, "Oh, the anisotropy that you are modeling is higher than what we observe." Yeah, one reason could be that my models are not entirely correct, and this might be true. The other reason might be that, you know, with the regularization, right, we can underestimate the real amount of seismic anisotropy. And in the central western Mediterranean, P-wave anisotropy appears to be distributed over the entire upper mantle, not just in the asthenosphere. This is another big discussion topic, with patterns suggesting mantle escaping from beneath retreating slab and sacked toward mantle wedges of the same or other nearby subduction zones. And the Mont Etna plumbing system appears to be characterized by a pressurized magma storage in a radial dike network in the 6 to 16 kilometer depth range. Thank you.